Okay, let's give day 2 a shot here. So, if you remember yesterday, we were looking at the fundamental theorem of calculus, and ideally we were just looking at part 2, which is what we did all today in class for homework. So we're gonna refocus on part 1 here. So I already have part 1 written here, and what it says, yet again, we have to have f as continuous. Then if we define some function g from a to x of f of t dt, we know the derivative of g of x is just going to be f of x. It's definitely a little confusing, so let's do some questions where we can be like, oh, okay, I think I got a feel for it. So let's do some examples here. So I'm going to say find g prime of x, and our question here is going to start off with if g of x equals the integral from 1 to x of t squared dt. So if we're looking for the antiderivative of t squared with respect to t, that should equal 1/3 t to the third from 1 to x. Plugging into this, we should get 1/3 x to the third minus 1/3. And that is just our g of x. However, we want to find g prime of x. So we need a derivative here. This first one just becomes x squared, and the next one 0. So we just have x squared there as our derivative. Now, if we look back at what the theorem says this derivative function should just be this inside function, but instead of with a t, it's just with an x. Isn't that what we just had happen here? Instead of this t squared, it's just x squared. And some of you may be saying, well, that seems very no duh. Why does that even matter? This just matters just for some of the fine tuning of going back and forth between derivatives and antiderivatives, showing that there is this true like bijection or one-to-one connection between them. Let's do some more examples and see what's going on before we just take those shortcuts instantly. Let's play the same question, except now we're from 1 to x of something maybe a little bit more elaborate. So we're integrating from 1 to x, t to the third minus 5t squared plus 4t dt, so with respect to t. So going through all of these, easy antiderivative, let's plug in our x and subtract here. And then we're subtracting a fourth minus 5/3 plus 2. So if we're taking a derivative of all these things, sorry, my notation's bad here. Our derivative here for this first stuff is coming just x to the third minus 5x squared. Oh, I did this one wrong. Sorry, that's a 2 there. Plus 4 over x. And then notice all of this stuff will just go to minus 0. They're all constants. The derivative of those is nothing. So our answer is just this function, except with x's up top. You might be saying, oh, those are really easy then. This homework should be pretty breezy. And for the most part it is. However, occasionally we will get questions that may look like this. Let's go from 0 to, let's stick with 1. I had a 1 there for a reason. From 1 to x squared cosine of t. Notice the difference here is we have something x to a power. It's not just pure x like we had in these other ones. And this is going to give one little nuance difference to us here. So as we're going through, we know the antiderivative here, sine of t. We still need to evaluate from 1 to x squared. So it's like sine of x squared minus sine of 1. But if we're looking specifically for the derivative, which is what we've been asked for all of these, the derivative here isn't just cosine of x squared, because we have to remember we need a chain rule in here, right? Here you should be thinking chain rule. So we still need the derivative here of x squared. And then, of course, the derivative of sine of 1, although we don't know what the number is, it just goes to 0. So our overall answer for this one, the derivative there, I'll put it out front, is 2x cosine of x squared. So anytime we have something to not an x power, when you take this derivative, it's like you're inserting that x squared in there, but you also need the derivative of this x squared, 2x, to pop out front. So whenever we see something with not just x here, that means we, in addition, need a chain rule derivative to match out front. So I'll show you how some of these should go and how quickly they should go, especially if we're looking at some tomorrow. This is a function that at this point we don't even know how to take the antiderivative of. But I know if I took an antiderivative, it goes up, and then I take a derivative right back, we know that the answer here should just be square root of 1 plus x squared. Nice and easy. Let's do 2 more. Sine of pi t squared over 2. Again, this is some big, complicated, clunky thing to find the antiderivative of. We could do it. It would take us some time. But we know if we're taking the antiderivative and then deriving it immediately after, this should just be sine of pi x squared over 2. Pretty easy. Then this last case scenario we had where it's not just an x you're going to. If in this instance I chose it to be, what did I have here? 1 to x to the 4th. Let's say secant of t dt. We need to take an antiderivative here, which would get us some function that we don't know right now for secant. But we know if we then take the derivative after, it's going to be secant. You have that x to the 4th in there. But we still need a chain rule. So you're going to need the derivative of x to the 4th as well, which should leave us with this as our answer. So hopefully kind of straightforward for what to do here. A lot of it may seem no duh, right? An antiderivative brings us up. A derivative will bring us right back down. So we just have to be careful of chain rules in effect here. So what we're looking at tomorrow for homework, we're in 5.3. These go pretty quick. So 7 through 18 I think is okay. And then let's see if we can actually finish up those ones from today, 31 through 37. We're going to see if we can get all those on the docket. Okay. Thanks, guys. Have a good rest of your night. I'll see everybody tomorrow in class.